Hello, everybody. Welcome back to our next lecture. Hopefully you guys have had a good weekend and are in good spirits. We're going to look at, we started talking about parameterized curves. The last lecture I gave you was pretty much a review of what parameterizations are. We looked at a few particular parameterizations. We built a parameterization with some specific conditions. And now that we have the ability to parameterize curves, we want to address some of the issues that are relevant and that calculus can deal with. So how do we apply what we've largely learned in our differential and integral calculus course to this new context of a parameterized curve? So that's where we're going to start today. And just to walk through this with you, I know you have a copy of these. These are the big issues, right? Tangents to a curve, right? That's an issue. If you have a curve, what's an equation of a tangent line? Related to that are things like instantaneous rates of change. Also, the length of a curve. Can we find arc length given parameterization? And then area under a curve, and finally, surface area that results from revolving or rotating about X, Y axis. Well, first, what do we mean by a parameterized curve? Well, we talked about what that is in the last lecture. Let's add to that notion now and talk about differentiability, right? So notice that you've got, first of all, two functions, a function for X and a function for Y. And while t doesn't have to be time, I think it's a natural way of kind of thinking about this and wrapping our heads around it, because you picture this particle in motion, and as soon as you picture it in motion, right, there has to be some time component. So you've got the x coordinate governed by some motion, and you've got the y coordinate governed by some function, and together, right, we get this curve traced out. And so differentiability at a given point means that both of these individual equations or functions f and g are differentiable. And of course, we can just call the entire curve differentiable if we have differentiability at every t in the domain. And then finally, smooth. What do we mean by smooth? Well, this means that the derivatives themselves, f prime and g prime, are both continuous. They are also not simultaneously zero, okay? So that's what we mean by a smooth curve. And if you think about what smoothness looked like before, right, you don't want any cusps or things like that. Okay, so recall that in a Calculus 1 course, a typical problem is finding the equation of a line tangent to a curve. And so to do this, we need slope, right, DYDX. But here's the problem. How do we find DYDX? Especially given the fact that y might not even be a function of x when the function is, or when the curve is given in parametric form. Well, we have this nice little formula. dy dx equals dy dt over dx dt. And really, I mean, you could think about some algebra here, right? dy dx, if you think about it, right, we have this expression, dy dt. Well, what does division really mean, right? Well, we're multiplying by the reciprocal, right? And so sure enough, you're left with dy dx, okay? And so this is nice, right? dy dx is just dy dt over dy or dx dt. And so we can now address this very standard or typical Calc 1 problem. Find an equation of the line tangent to the curve x equals cosine t, y equals 1 plus sine t at t equals pi halves. Well, let's first, right, we're finding the equation of a line. So what do we need? Well, just like any line, we need a point. Well, where will that point come from? We know what t is, and we know based on t what x and y are. So the point is going to be cosine pi halves, which is 0, and then y, 1 plus sine pi halves. And of course, sine pi halves is 1. So 1 plus 1 is 2. So the point we have is 0, 2. That's kind of nice. This point's actually the what? Yeah, it's the y-intercept. All right, the next thing we need is slope. Okay. And so we need DYDX evaluated at the point 0, 2. Well, that's going to be dy dt over dx dt, evaluated at the point 0, 2. Okay. I'm sorry, not at the point 0, 2. Evaluated at what? That's right, t equals pi halves, which corresponds to the point 0, 2. So dy dt, the derivative of 1 plus sine t. So the derivative of sine is cosine. So we have cosine t over, and then the derivative of cosine is negative sine. So negative sine t. And if we evaluate this at t equals pi halves, what do we get? Well, we're going to get 0, right? And so the equation of the tangent line hopefully you don't hear that dog barking. Think of it as the kids walking up to the planetarium. All right, so we have the point. So y minus 2 equals 0 times x minus 0. Don't need to go through all that if you don't want to. I mean, you recognize that the slope is 0, given the y-intercept. So we have the horizontal line, y equals 2. Okay. All right. The next issue is finding the length of a curve. And so we have this expression here. Again, x and y are given as functions of t, and this becomes my formula for arc length. Now, I want you to notice, right, it's traversed exactly once on AB. What we don't want to have happen is that maybe this is t equals a, and the curve, I don't know, does something like this and goes around again, and maybe this is t equals b, right? We wouldn't want that. If you want to think about it in terms of like a circle, right? If we were finding the circumference of a circle, we would go from 0 all the way to 2 pi, right? But what happens if I went from 0 to, say, I don't know, 3 pi? Well, I would get the circumference plus a little bit more, right? Because I'm traversing this curve more than once. So we don't want that to happen, right? So that's why we're saying that we only have that traverse one time, okay? So it's not going to come back on itself, if you want to think about it that way. It's not going to go back over itself or something. And so here's our arc length formula. Well, let's recall our previous arc length formula. I mean, after all, arc length, right? We know how to find arc length when y is a function of x, and at least locally, could we think of this as y being a function of x? I mean, what do we mean by traversed exactly once? Seems like we might be able to. So before, arc length was this, right? 1 plus f prime of x squared dx. So how does this become that? sorry, I'm gonna give you a better arrow than that. How does this become that? That's what we want to look at, okay? So let's take a look at A and B. And instead of looking at this as f prime of x, maybe I'll call this DYDX. dx, okay? And we know that DYDX is really DYDT over dx dt. Well, now what? Well, I want you to pause the video for a moment and just spend some time playing with this expression under the radical and see if you can't get what we want out of this, okay? And again, it doesn't have to be a long time, but please do pause the video and see just, even if it's just on scratch paper, just scratch some stuff out and just play with it a little bit, okay? And see where it takes you. And then when you come back, I'll of course have the rest for you. And I promise this won't traverse a couple days like sometimes happens in class. So again, give it a pause, play with it, and then come back to video, please. Have you paused it yet? All right, so let's go back and take a look. So hopefully you're able to play around with this a little bit. And let's just start by messing with the second term in the radical. So I'm going to treat this as 1 plus, and then I'm going to call this whoops, boy, let's try that again. dy dt squared times dt dx squared dx. Now, I mean, think about that. This is just some algebra, right? I've got my numerator squared over my denominator squared. Dividing by the denominator is multiplying by the reciprocal. So there I've got it. Now, I'm going to be a little bit creative here, and I am going to factor out a dt dx squared. Now, this may seem odd, like why would I be thinking to do that? But look what happens. My first term, well, let me go over to the last term here. So plus, when I factored out my second term under the radical, I'm just left with dy dt squared, right? And that's encouraging because that's what I want, okay? But then what does my first term become? Right, my first term is 1. So if I'm factoring dt dx out of 1, it's going to become dx dt, right? And so I've got a dx dt here. And if you need to, convince yourself, right? Distribute that. You know, these will all cancel. You'll just be left with 1. But it gets even better. Gets even better. Because dt dx quantity squared is under the square root, right? And so really, I get a dt dx square root of dx dt squared plus dy dt squared dx, and what do you know? We are left with exactly what we are told it should be. Dx dt squared plus dy dt squared dt. And technically these are different bounds, right? We're now talking about t's, not x's, so I'm not calling them alpha, beta. It's a minor point. Just wanted to kind of see how this thing developed. And so there we have it, okay? All right, so let's see how this works. We're gonna find the length of this asteroid over 0 to 2 pi. Now, you wanna be careful because, right, we know what this looks like. We saw that earlier. But I'm not gonna go from 0 to 2 pi because if you think about it like a displacement perspective, it's 0, right? I'm right back where I started. So instead, I'm gonna take advantage of some symmetry here. And I'm gonna say that the length is 4 times the integral from 0 to pi halves, okay? And then the square root of all that business dt, okay? And so let's look at dx dt, right? You get our hands on all these. So dx dt is going to be 3 cosine squared t, and then derivative of cosine is negative sine. So I'm going to throw that negative sign out front there. And there's my dx dt. And my dy dt then will be 3 sine squared t, derivative of sine is cosine, okay? Little chain rule there. So my length of that asteroid be 4 times the length from 0 to pi halves of the square root. And then we've got negative 3 cosine squared t sine t squared plus, and then my dy dt dt. And let's just kind of see where this takes us, right? So I've got a 4. Sorry, give myself some room here. All right, so 4 integral 0 to pi halves. And then what do we get? We're going to get a 9 cosine 4th t sine squared t plus 9 sine to the 4th t cosine squared t and dt. All right, now let's not get intimidated by this. Let's just kind of see where it takes us. So I'm going to factor out a 9. And let's see, looks like I can factor out a 9 cosine squared t, oh, sine squared t. Well, that's nice because that's a nice perfect square. And then times, well, let's see, what is this first term going to give me? Oh, it's going to give me a cosine squared. Ooh, I am getting hopeful. Plus this, oh, it gives me a sine squared. I love it when that kind of thing happens. dt. And so, of course, this piece is just 1. And so I have 4 integral 0 to pi halves. And then take the square root here, and you got 3 cosine t sine t dt. And this is a lovely problem you might even see in like a Calc 1 course, because I can just bring that 3 out if I want. I'm not going to yet. Let's do a u sub, right? I'm going to let u be, I'm going to choose u to be sine. So du would be cosine t dt. And now my bounds I need to adjust as well. And here's where you need to be careful. Remember at the beginning I said let's go from 0 to pi halves so that we don't accidentally go from 0 to 2 pi and think of our displacement as having been 0, since we're coming back to where we started. Here's the deal. If I'd gone from 0 to 2 pi, then sine of 0 is 0 and sine of 2 pi is 0, which means I would have been integrating from 0 to 0. And so that integral will just be 0, but we know that's not accurate because we can see it's arc length, right? So I was smart to go from 0 to pi halves. So let's see here. U of pi halves is going to be 1. U of 0 is 0. I'm not sure why I did that in reverse order, but okay. So what do we get here? We get 12 integral from 0 to 1, and then u du, which is 12 u squared over 2, 0 to 1, which is going to be what? 12 times 1/2, and so we get 6. Okay. There we have it. All right, next we want to look at area under a curve. So that's going to be our next little mini lecture here.